Okay, so we discussed the response spectrum, the the concept of the response spectrum, and then some of the past work carried out by for the development of response spectrum using instrumental approaches and then also using the theoretical approaches. Now the next one is the work carried out dealing with the response spectrum through the computation. So we will discuss the past work carried out in order to compute the response spectrum. Okay. So mainly computing response spectrum. So although the concept of the response spectrum was introduced in the mid 1930s and was matured in 1941, so we already mentioned it. But at least for the undamped system, but it took additional 2 more decades to develop various methods in order to determine response spectra for recurrent ground motions. And of course, the method earlier to the computation methods were all became obsolete. So all this method uh, regarding the response spectrum development using instrument or using theoretical approach, they were all obsolete when the computation methods were introduced. So let me mention is that all they became obsolete with the advent of digital computers. And actually, because of the lack of computers, determining the earthquake response spectrum was a formidable task for several decades. I mean, it was quite difficult to do the computation for the response spectrum development using the daytime computers. When actual accelerogram became available, for example, starting with the 1933 Long Beach, Long Beach earthquake in California. So this was the first earthquake which was available, which was recorded using the, uh, which was digitally recorded using instrument. And so this helped us a lot in, this helped us in the development of the response spectrum for digitally recorded accelerograms. Okay. Now, obtaining 1 point on the spectrum required the determination of the response of a single degree of freedom system to a given ground motion acceleration. We already know this, that for the elastic response spectrum, if you want to develop just 1 point, you have to completely analyze a single degree of freedom system by subjecting that to an accelerogram and then recording the peak response of that and then plotting against the vibration period of that system. And if you do that for a number of accelerogram, for a number of for a number of SDF system with different vibration period, you will develop the response spectrum for that accelerogram. Now, at that time, using even the numerical approaches, the response of the SDF system was determined in several ways. For example, there was a procedure which you have studied probably in the and also in the structural dynamics, was the numerical evaluation by Duhamel integral. There was graphical integration. Okay, this was a method used by Newman using instrument called as Integraph. And at the same time, for the computation, there was Shake table that was used by researcher at the Stanford University. So I think this was some kind of, you can say, the first experiment using the Shake table for the response analysis of very single data freedom system. So this was at the Stanford University and was used by Jacobson, was a very famous structure and earthquake engineer, and Hoff. At the same time, beside these, there was also torsion, pendulum, those mechanical analog devices similar to the analog device similar to those developed by Husner and Biot. Also, Husner, who work on the development of response spectrum using those torsion pendulum, he actually upgraded that mechanical analyzer and upgrade that electrical to the electric base analyzer. Okay, now the main difficulty involved in the mechanical torsion pendulum was that the time period and the damping was fixed, okay, in most cases. So these were the problems, that the period of vibration or the damping for a given system, it was constant, or you cannot change them with accuracy. So those were like challenges for the mechanical torsion devices to take into account the variation in the period as well as in the damping, and also to get the target damping and time period with these instruments. These difficulties, they were overcome by another improved system that was developed again at the Earthquake Research Institute in the Tokyo University, and and that there was a scientist who introduced a moving coil galvanometer. I don't know if you studied these in basic physics, but there were these instruments that were produced and were used for the response analysis of various single degree of freedom system for accelerograms. And after the World War II, as I mentioned that Husner again upgraded his mechanical torsion pendulum and converted that to an electric based analog instrument. And they greatly speed up the process and increase the accuracy. So what Husner did, he converted the torsion pendulum mechanical based to electrical. Electric powered base. Okay, and the work carried out in this era, these were like they developed various response spectra that included spectra for various damping values. So like spectra for a variety of damping. So the availability of digital computer in the 1950s, it motivated the development of numerical methods, basically solving differential equations with a much more efficient way using numerical approaches in comparison to the Duhamel integral. So like this was the time time when numerical approaches were introduced to solve the differential equation, the dynamic equation that we mentioned in the previous slides, that was solved by numerical approach rather than the Duhamel integral. Okay. So what happened? There was a landmark paper written by Newmark. So Newmark presented an idea in 1959 where he proposes numerical method for structure dynamics. Okay, so solving the differential equation using numerical Newmark method. Now, coming to some discussion related to the true and pseudo spectra, because we mentioned also the true response spectrum, and we also talk about the pseudo spectrum. Actually, there is a little motivation to mention the relative velocity response spectrum and the actual response spectrum because these true spectra are not needed to determine the peak deformation and forces in system. So the true spectrum is not really needed. Okay, so whenever, for example, we are using the building code spectra, it's not the true spectra. So you can see that what we are using today is the pseudo spectra or the idealized spectra for the design. So what we do is that we use the pseudo spectrum, and the pseudo spectrum is sufficient for the design of structure. So once you do the design, you can then check with the real earthquakes, and you can see that it is sufficiently accurate. So there is no need to use the true spectra. So we prefer to use pseudo spectrum. So let me mention that pseudo spectrum is sufficient for the computation of the peak response. Later on, a lot of researchers carried out some work on the comparison of the true spectra as well as the pseudo spectrum. And it was around the late 1960s that some work was presented in comparison to this. Okay, and the similarity and differences between the two spectra were highlighted. So what was observed at that time that the pseudo velocity spectrum is a good approximation to the relative velocity spectrum, with the quality of approximation improving as the system damping decreases. So as you mentioned, the V velocity spectrum was found to be very much close to the actual relative velocity spectrum when the damping is low. So I mentioned here for low damping. Okay, today we consider that the pseudo velocity spectrum is the preferred system because it provides directly the peak deformation and the base shear. So like today we prefer more this spectrum, the pseudo spectrum, because it directly provides you the peak deformation and the base shear force acting on the structure. Uh, Back in that time, Willett Sows and Newmark, these are again some researchers at the UIUC, at the University of Illinois, in Newmark. They compare true and pseudo spectra over the complete range of period right from 0.04 here from 0.04 second up to 25 second. Okay, and what they found is that both spectra are closed over the medium period range. For short period, the pseudo velocity is greater than the relative velocity, the actual response, the actual true relative velocity, short period. And for long period, the pseudo velocity was less than the true velocity. And also at that time, the work was also carried out for the acceleration response spectrum. And it was found that the acceleration response spectrum, the pseudo and the actual spectra, they were shown to be identical for undamped system. But the difference increased as the damping increased. So the absolute, the pseudo spectrum was similar to the relative, the total actual true response, acceleration response spectra was similar for an undamped system. Okay, but when the damping increases, the difference increases. Okay, so let me mention here. So the difference increases as damping increases. Okay, this difference was small for short period. So for short period, it was small, and for long period, the difference was significant. Okay, now some discussion related to the Fourier spectrum and the pseudo velocity spectrum. Okay, so the Fourier amplitude and the phase spectra do not only show the frequency characteristic of the ground motion, but the system response can be calculated using Fourier integral theory, leading to the well-known response analysis procedure via the frequency domain. Okay, so you can do the frequency domain analysis. So for example, if you are doing some dynamic analysis, so one is like to look at the numerical procedures, the numerical integral, numeric integral procedure, the numeric, the numerical approaches for the analysis of uh, the dynamic equation. But there is another way is to use the frequency domain analysis. Okay, what you do is that you convert input to the frequency spectrum or the Fourier amplitude spectrum, and also the building response is also represented in terms of the uh, transfer function or the response of the building in the frequency domain. The convolution of these two or the multiplication of the two give you the response. in terms of the frequency domain, and then you convert that in time domain to see how the time variation can give you the response of the structure. So if you study structure dynamic, there is a discussion about the frequency domain analysis. But mainly the Fourier spectra in Beck was used only to convert the time signal recorded for the earthquake into the Fourier amplitude. Okay, and it basically gives you an information about the energy content of the accelerogram along the frequency. So it gives you a picture of how much energy is present in an accelerogram and at which frequencies it's dominating. On the other side, the response spectrum has been preferred for structure engineering application because it contains both the frequency properties of the excitation and the structure parameter influencing the response. So frequency domain or the frequency amplitude, the Fourier amplitude is just the giving you the idea of the frequency content of the input. But the response spectrum is giving you information both on the let's say vibration period or the frequency of the input and also the response of the system. For example, if you develop response spectrum, you know what is the vibration period of your system. You can directly obtain what will be the demand on that system. If it is acceleration response spectrum, you can get acceleration. If it is velocity, you can get velocity. And if it is a displacement, you can get the displacement response. So it can give you both the frequency content as well as it give you the response quantity. But the frequency or the Fourier amplitude spectrum is not giving you the response quantity, but it only just giving you the frequency content and the frequency content, the energy content of the accelerogram or the input motion. The Fourier amplitude spectrum is identical to the undamped relative velocity response spectrum for some special cases. So in some special cases, the Fourier spectrum and the relative velocity spectrum they are identical if the you are looking at the response of an undamped system. Okay, but these are for some special cases when the peak response of the accelerogram occur at the very end of the ground motion. Okay, but in reality, the peak response mostly occurs somewhere in the mid or maybe in the earlier of the start of, or let's say the start of the accelerogram, or somewhere in the middle of the accelerogram rather than at the end of the ground motion. So in majority of the cases, the velocity response spectrum exceed the Fourier spectrum. Okay, so if you look at the undamped relative velocity spectrum, uh, the amplitude is always more than the Fourier spectrum. Now coming towards some response spectra characteristics. We talk about the acceleration response, velocity response, as well as the displacement response. But let's talk about some of the characteristics of these three. What information we can obtain for structures if we know their velocity, acceleration, and displacement responses. So there was a report by Willitsos in Newmark, again from UIUC, that looked at the various properties of acceleration, velocity, and displacement response of the various single degree freedom system. And what they did is that spectra uh, were integrated presentation showing all these response quantities. So when I say response quantities, I mean the displacement, velocity, and the acceleration. And what they did is that they plotted on the a three-dimensional logarithmic uh, graph paper, which they called as which is called as tripartite. I think you can correct me if you know the exact tripartite logarithmic graph paper. So this was a logarithmic graph paper, and it was tripartite because it was showing you three quantities on one plot with respect to the frequency. So let me just show you how it looked like. For example, if this is the vertical axis, this is the horizontal axis. So let me just plot something. The combined spectra look something like this. Okay, so there were some, let's say, vertical lines, which was representing the frequency, the undamped natural frequency of the system. And on this vertical axis was the velocity, but normalized by the ground velocity of the input, and this was the velocity of the single degree of freedom system. And they were parallel line with a 45 degree like this. So let me just do it with other colors. Okay, right. So these lines like this with a 45 degree, these were for the displacement, and it was represented by d divided by the ground displacement. So it was normalized by the, this was, sorry, this is not velocity, so this is just u, not u dot. And there were these 45-degree lines here, which was for the acceleration divided by the ground acceleration. Okay, so this plot was having the advantage to provide you all the three values, just knowing only the frequency of vibration, the vibration period, or the cyclic frequency of the structure. Okay, and it also, if you look at such plot for a number of single degree of freedom system, let me plot it here again. What Newmark did is that they developed this kind of spectrum for a number of accelerogram, and what they found. So let me just give you detail. This is what they saw. Okay, so this is what they receive or look at the observe of those very single degree of freedom system. So what they observe? They observe that the system with very short period, which means somewhere here in the longer frequency means shorter time period. So in these very short period, the pseudo acceleration or the acceleration approaches the ground acceleration, which is true. When the time period is very, very low, the acceleration acting on a structure is exactly equal to the ground acceleration. Okay, and if it is a very long time period or a very small frequency, the displacement demand on the single degree of freedom system becomes equal to the ground displacement. Okay, and you can see that these lines are getting closer to each other, so there is no difference between the ground displacement and the structure response displacement. If you look at this plot, it is also giving you a quick view of three regions. For example, this region, then this region, and this region. So this is what is called is the acceleration sensitive region. This one is the velocity, and this one is the displacement sensitive region. Okay. In fact, in these region, the acceleration, like in here, the response of the system is mostly or closely related to the acceleration. Here, it's closely or mostly governed by the velocity, and this is mostly governed by the displacement. Also, if you look at the spectrum, you will see that damping, if you, because these spectra are developed for various damping, and you can see the damping is increasing in this direction. So this is increasing damping. So if you increase damping, this is what you see. Okay, so if you increase damping, it is mostly affecting the velocity region. Okay, but if you have more damping in a let's say in a displacement sensitive region, or you have more displacement, more damping in a acceleration sensitive region, it has less effect. So it's only effect only here. So I mean, this is something very fundamental to give you a sense that if a structure is in the displacement sensitive region, you don't need any damper devices to control the demand. And also, if it is in an acceleration sensitive region, the dampers will not help you. But if it is in a velocity region, it can help you a lot. Okay, so this was all for the today's lecture. If you have any question, you can let me know. We can discuss. Okay, just to give you an idea, so that you can also recall that in today, in the modern code, how the spectrum is represented. So you see there is a linear branch, then there is a plateau, and then there is a decay branch. So in UBC, this is the kind of spectrum that is represented. This side you have the time period, and on the Y side you have the spectral acceleration. So you have SA with respect to the time period. But if you look at the IBC, so in IBC there is also a fourth branch. Okay, in UBC it is just increasing with the same trend, but in IBC the trend changes at a time period that is called as TL. So there is also a corner time period, or a TL, where the spectra changes its behavior or the shape, and it reduces by a t square rather than a t, which is basically decaying in this branch. Okay, so again you can see that this region is what is called as the acceleration sensitive region. This is the velocity sensitive region, and the other one here is the displacement sensitive region. Okay, so this lecture was a kind of an introductory lecture, just to understand about some of the basics used in the earthquake engineering and in the structure dynamics, in the development of the elastic response spectrum that is later on used for the analysis and design of structure. If you have any question, you can let me know. Okay, so if there is no any question, I think I have to close at this point, because this is what I wanted to mention here for this introductory class.
Excuse me, sir.
Yes.
सर इसके स्लाइड्स मिलेंगे?
Yes, of course. This is for you.
Okay, sir.
I have prepared some notes as well, so I can share the same with you as well.
Okay, sir.
Okay, so if there's no any questions, so what I will do, I will close this discussion and we'll see you next week. Okay, good luck.